going to be talking about more RTX 50. What is this? Today we're going to be talking about MFG and image quality for DLSS 4. We're comparing the image quality of fake frames today, frame by frame, along with DLSS 4 models. Frame generation serves as a smoothing solution between frames. Because it's artificially generating frames to insert, we can regularly observe issues where not all fake frames are created fake equal. In this frame by fake frame, you can see issues with trailing or leading edge objects in motion as they leave ghosting or sparkling in their wake. In some instances, user interfaces distort and duplicate during fake frames. And during multi-frame generation, during multi-frame generation, sorry, I didn't say that right. I didn't say that right. Anyway, let's just, this intro's really jumped the shark. Let's just move on. There are a lot of situations where things have improved with DLSS 4 as well. In some, we see better than native image quality. That's good for NVIDIA with the newer transformer model, such as in games which force TAA. We also saw that thin objects like barbed wire and tree branches sometimes look better with the new model than with the older model for DLSS. But there are areas where DLSS needs improvement as well, such as in some scenarios with distortion around the text. Today we're evaluating DLSS 4 and multi-frame generation, all right? It's a different one than the other MFG that everyone's talking about for image quality. So we're gonna go frame by frame and look at MFG today. We're also gonna do a model comparison between CNN and Transformer. As an important reminder getting into all of this, remember that we're intentionally zooming and slowing things down a lot. So that means it's really important going through this. This is just, methodologically, we gotta go frame by frame and really slow it down and zoom and inspect to see the differences. But remember and keep in mind that the sort of situational awareness of you're playing these games at full speed, you're probably not gluing your eyes to like a specific quadrant of the monitor. And so in real time, some of these differences we're gonna look at today, they might not be noticeable to you. And so we're gonna have sort of full speed zoomed out footage occasionally as well. That'll be your opportunity to look at it, see if you can spot the difference in real time playback. Something really important to remember, which is that we are zooming in and trying to spot differences as what this content actually is focusing on. Doesn't mean you're always gonna see them. So let's get into it. Before that, this video is brought to you by Thermal Grizzly and their new Duronaut thermal paste. Thermal Grizzly claims its Duronaut paste is intended for long-term stability and endurance, focusing on paste longevity in addition to the usual performance focus. Thermal Grizzly's Duronaut paste comes with applicators and spreaders, and ships in numerous tube sizes, aiming to provide a high-end paste for PC builds and daily driven overclocks by enthusiasts. Learn more at the link in the description below. All right, so for testing, we used the latest public driver at the time we did this testing, which then was 572.16. We used mostly a 5090 for all this. We had a 5080 for some, doesn't really matter for what we're comparing. And we used public releases of all the games tested. And so we matched the true day one user experience for all 6 of you who got a video card on day one. And hopefully the bots enjoy this video. Now, we'll check in with Patrick and Jeremy throughout this piece. They both worked on writing and testing, did the bulk of the work on all of that side of things. They're gonna introduce their sections. Let's check in with Patrick first.
Our previous DLSS 4 piece covered performance. To summarize, the move from a CNN model to a transformer model for DLSS super resolution and ray reconstruction comes with a small hit to performance. Generally, the older CNN model is 5% ahead in performance, but the new transformer model should look better, which is what we're going to get into here. Conversely, the move to a new frame generation model utilizing tensor cores comes with a small uplift in performance, but hopefully no change in image quality, which we'll also check. Finally, we'll look at some MFG 4X AI-generated frames to see if they look any different from the old FG 2X frames. Since this piece is only covering image quality and not performance, we were able to use local capture for all of the recordings. We could use OBS for the DLSS super resolution and ray reconstruction capture, but we were forced to use NVIDIA's app, formerly known as Shadowplay, to capture the frame generation because OBS couldn't reliably capture the generated frames. As for DLSS super resolution, Jeremy handled the first section of that.
Okay, Now we'll compare just super resolution in isolation without any frame generation. We're going to do that so we can look at the difference between the old convolutional neural network model and the new transformer-based model. NVIDIA says that it, quote, reached the limits of what's possible, end quote, with CNN, and that the transformer model provides a stronger foundation with headroom for improvements over time. NVIDIA says, quote, the new model uses a vision transformer, enabling self-attention operations to evaluate the relative importance of each pixel across the entire frame, for multiple frames, end quote. It supposedly has a better understanding of what's more important in a given scene, culminating in what NVIDIA claims as greater temporal stability, reduced ghosting, higher detail in motion, and smoother edges. NVIDIA boasts particular improvements to ray reconstruction in scenes with what it says are, quote, challenging lighting conditions, end quote, such as better stability when looking through a chain link fence when moving, and reduced ghosting on fast-moving elements like fan blades. We'll check for these specific claims in addition to general image quality comparisons. As a last note before we get into these, some of the examples we're going to show focus on very fine details or background elements. It's often not a huge difference when you're comparing the models to each other, and represents more of a trade-off between the two. Sometimes it's notable though. Let's go to Steve for the comparisons.
Final Fantasy XVI is up first for CNN versus Transformer comparisons and has driver-level model overrides via the NVIDIA app. At native resolution, it forces anti-aliasing with a faint temporal effect, sometimes visible on the trailing edge of objects in motion. To our knowledge, using DLSS Super Resolution disables the game's native anti-aliasing. The first scene we're looking at is when a Dragoon, with a familiar sounding voice to anyone who's played Final Fantasy XIV, falls out of the sky to fight. As the Dragoon poses against the sky, we see a lot of areas of contrast between lit and unlit sections of armor. The helmet and shoulder armor are noticeably clearer with the new Transformer model. This is the most obvious in more defined edges of the dark slits on the face of the helmet and in the worn surface of the curved portions of the shoulder armor. The brightly moonlit scales of the chest armor show far more definition, with the Transformer model bringing a sharper look than the prior CNN model. The same effect is visible on the inside of the cape, where at first glance, it seems like there's a higher quality texture or something. The CNN model gives a softer impression to the fabric compared to the coarse looking version with the Transformer model. Subjectively, it's up to you which one you think looks better. After the Dragoon lands and the player is knocked back, we see the first real failure of the new Transformer model. When the character spins around, there are several ghost images superimposed over the background dust as the character extends his sword. We also see a situation where both DLSS models drop the ball as the player's sword whips past the chainmail sleeve. Before it moves past, both the CNN and Transformer models appear slightly lower quality compared to native. After it passes, the non-native models fall apart. The CNN model turns the chainmail to mush, and the metal band loses much of its definition. The Transformer model, meanwhile, keeps the mail together better, but at the cost of massive and obvious ghost images of the sword that stay behind for a few frames. Directly after that, the sword moves across the arm again, leaving a bad smear behind it. This example is among the worst that we'll look at. Considering that NVIDIA specifically mentioned less ghosting with the new Transformer model, it's not a great start. It's starting to look like the model switch isn't just a straight upgrade and comes with trade-offs. In this goblin chase scene, DLSS with the Transformer model does a better job of holding together the detail on the metal emblem on the sword's scabbard. The ground also looks clearer and less hazy. Focusing on the goblin on the rock shows that, despite the increased clarity, the Transformer model is leaving trails behind as it moves. Interestingly, as the goblin jumps off the rock, there's no visible trail or ghosting. This could make sense if motion vectors are part of the equation, and NVIDIA says that it uses motion vectors as part of the equation for both frame generation and super resolution. Additionally, the new self-attention operations that attempt to evaluate relative importance of elements within the frame could also be playing a role. The last Final Fantasy scene we're looking at is the hideaway. Focusing on the pillar to the left shows that the Transformer model is again noticeably clearer than the CNN model during motion. Subjectively, there's room to think the Transformer model looks better than the native capture here. It comes off as adding clarity to both the sigil on the stone and the small bags at the base of the pillar. The staff leaning against the shelf also appears more distinct than both the CNN model and native. Subtle and faint temporal artifacts around the player's legs are visible with both DLSS models, as well as in the native capture with anti-aliasing. Looking past the horizontal beam wrapped in rope shows both DLSS models struggling relative to the native capture. but the smearing and ghosting are worse on the transformer model. This follows the same pattern we saw in other scenes. It's a fine background detail, but on inspection, it's unmistakably worse. Cyberpunk 2077 is next, tested using the in-game toggles rather than the driver-level override. Cyberpunk forces temporal anti-aliasing, or TAA, at native resolution, resulting in some unstable or soft visual. First, we'll show a scene where the player jumps, causing a barbed wire fence in the foreground to rapidly move across the background. As soon as motion starts, the barbed wire itself loses a lot of definition with both DLSS models, but the transformer model does a better job of keeping it together visually. You can see the detail difference particularly in the barbs on the barbed wire, with the pixels immediately surrounding them experiencing the most change. The buildings behind the wire also look better with the transformer model. The CNN model gives an almost clay-like Play-Doh appearance with motion, giving a melted effect to an otherwise solid structure. In the next scene, an NPC is dancing in front of a wall with a lit pattern of thin lines. Native capture with Cyberpunk's forced TAA struggles hard, plagued by ugly temporal ghosting artifacts that take forever to resolve. The users over at /r/TAA might have a valid point. Yes, that's an actual subreddit, by the way. It's embarrassing for the game to look this bad at native 4K, and CDPR should let players turn this off or choose another anti-aliasing method. In the DLSS comparison, the transformer model handles this situation the best, we think. It quickly restores the alternating horizontal and vertical lines as the NPC moves in front of them. This is a clear win for the new model. Here's the highway outside the Sunset Motel at dawn. We'll zoom in on the wires between the billboards. As the player drives forward, the CNN model shows obvious smearing that's greatly reduced when switching to the transformer model. As we pass the Sunset Motel, we see reduced ghosting on the sign and wires against the sky, as well as more stability on the palm trees. Both of the games we've used so far have more realistic art styles and tend to favor dark scenes with lots of detail. In contrast, we'll take a brief look at Marvel Rivals, a competitive third-person FPS with bright colors and a more stylized aesthetic. We used the Ultra Graphics preset and left the unusually high DLSS sharpening default of 80 unchanged. To get a controlled environment, we jumped into the practice range. The character select screen showed no meaningful difference between the two models outside of a mild sharpening effect with the transformer model. As we run forward and engage the target dummy, we see that the character models in the foreground don't show a noticeable difference when switching between CNN and transformer, or at least not one that matters. However, things in the midground and the background get a boost in clarity from the transformer model. This includes the enemy bots, the stairs, and the hanging purple tapestries. We suspect the high default sharpening is lessening the visible impact between the models. Ghosting is improved, as seen here on Mantis's arms during her ultimate, as the transformer model keeps the image more stable. Up next is frame generation. This section's pretty interesting. So using the NVIDIA app, our maximum capture rate at 4K is 120 FPS. This means that with MFG 4X, in order to have the best chance of capturing all the generated frames, our render rate can't exceed 30 Hz. We primarily captured with 30 Hz render rates, which allows us to compare how the different frame generation settings bridge standardized frame-to-frame intervals of 33.3 milliseconds. We can then do frame-by-frame comparisons or playback at 50% speed. Real-time 120 FPS comparisons are not possible in a 60 FPS YouTube upload. Frame generation works better with higher input frame rates, and its main advantage is looking smooth on high refresh displays. But this is the best compromise available to us right now. This is something that's very difficult to convey remotely to people because it's such a localized thing to study. We had a ton of issues with the NVIDIA recording app, like randomly resetting the recording bitrate and lacking a way to directly choose H.264 or HEVC. Worst of all, the app occasionally broke frame generation in game altogether, delivering generated frames out of order, which you can see here. This may have been related to another issue where the driver level overrides broke completely, not applying anything above MFG 2X and requiring a driver reinstallation to fix. Not good. Again, all of this was on public consumer software and public consumer hardware, if you can find one, if you're one of the bots that got one. All right, so there's still some confusion about MFG, and we'd recommend watching our first DLSS 4Ps to get that baseline explainer. NVIDIA's original frame generation could generate up to one fake frame to be inserted between rendered frames. while the new MFG can generate up to 3 fake or synthetic frames to be inserted, or as NVIDIA calls them, AI frames. It's natural to be annoyed that NVIDIA is bragging about an even higher percentage of fake generated frames. But it's also important to remember that in terms of time, those 3 fake frames slot into the same space that the one would have previously. The percentage of synthetic frames goes up from 50% to 75%, and that opens up a lot of quality concerns that we'll look at. But the real frames that bookend them are delivered at, ideally, the same rate, although frame generation does have some performance overhead. All the games we're using for FG comparisons support NVIDIA driver overrides, since that allows us to test the old model. The clip being shown right now was recorded with maxed out settings, no upscaling, no anti-aliasing, no VSync, and a 30 Hz in-game render cap, which is intentional. Other post-processing effects like motion blur, vignetting, and bloom were turned off to make comparisons as clear as possible. This is the baseline series of native frames being fed into the frame generation algorithm. Using the new frame generation model at 2x, 1 frame is generated for every 1 rendered, so 30 FPS input should equal 60 FPS output. There are a few skipped frames due to the capture method, but we grabbed most of them. You can see that the frames are updated twice as often as they were at baseline, but every other new frame has the telltale signs of generation. In particular, the fast-moving raindrops are well-defined in real frames, but fade away in synthetic ones. This means that, in motion, the raindrops have less contrast and fade into the background more. Similarly, the sharp lighting on the buildings in the distance is smeared out in fake frames, although this would be less noticeable with anti-aliasing applied. Thin tree branches become blurry as well. These artifacts only appear in motion. If nothing moves between frames, then frame generation doesn't need to make any guesses. This is a slow-moving scene, but we can see hints of another problem, which is the reverse ghosting caused by frame generation. On the left side of the player character and the railings in the background, you can see outlines where these items will appear in the next real frame. Other than an overall smoother feeling, this is probably the biggest area where MFG has an opportunity to improve over the existing FG2X. Because of the slow movement in this scene, playing back 2x and 4x captures side by side, even at 50% speed, doesn't reveal obvious differences, although differences do exist. The raindrops may have slightly lower contrast at 4x due to the higher proportion of AI or synthetic or fake frames. But as we'll see later, not all MFG frames are created equal. We're moving faster in this scene, which presents more of a challenge for frame generation. We'll start by comparing the baseline 30 FPS pass without any frame generation to FG2X. The clear areas of difficulty here come as the player character vaults over the rubble, with frequent artifacts on the leading edges of the character's sword and legs, culminating in some frames where the legs get completely blurred. Subjectively, we find this hard to notice in actual motion at actual playing speed. Running across a complicated background of cobblestone and wooden boards leaves a noticeable trail behind the player's boots, with blurry streaks of shadow and light that don't quite keep up with reality. When played back at 50% speed, the effect is marginally more noticeable with MFG 4X. We can't sync up the random lightning flashes here, so we'll move on to a different scene for that. Moving to this scene on a hill, we can take a closer look at how MFG 2X and 4X handle the single frame transition of a lightning flash. MFG 4X shows 3 frames of incorrect data versus only 1 at 2x as it tries to slowly ramp into the flash. But each set of incorrect frames is displayed in the same window of time, so the appearance in real time is near identical. This is a perfect academic example of a frame generation failure, but it's not one that's obvious during gameplay. For these Final Fantasy XVI comparisons, we were forced to enable DLSS SR in order to enable frame generation, so DLAA was enabled for all of these captures. Otherwise, the settings match the ones from our DLSS SR testing, with post-processing effects like motion blur, vignetting, chromatic aberration, and bloom disabled. Now that we've covered some of the shortcomings of frame generation in general, we'll focus on 2x versus 4x. This scene involves sprinting through alternating patches of bright light and shadow, which creates the first situation in which frame generation looks bad enough to be immediately obvious to us, even at full playback speed. There's significant artifacting trailing behind Clive, but also bright outlines around his arms as they swing in and out of the light. The worst case still frames are similar at 2x and 4x, but our team thought 4x looked worse in motion. Moving to a segment of the MFG 4x capture where we successfully caught every generated frame, we can go frame by frame and demonstrate what we meant by not all frames being created equal. Keep an eye on Clive's boots here. This first frame is real. The second frame is fake, but visually close to the first. The third frame is a complete blur. The fourth starts to come back into focus, and the fifth is a second real frame. The generated frames that fall closer to keyframes are clearer. In the scripted Dragoon scene, we can see how frame generation struggles with movement around UI elements. You might have noticed something like this before when scrolling through settings menus with FrameGen enabled. The generated frames heavily distort the UI as the motion passes behind it, then duplicate the health bar and the text during quick pans. Both FG2X and 4X show the same artifacts, but since 4X has synthetic frames on screen for a longer proportion of time, the artifacts are visually sustained. Going frame by frame reveals the shortcomings of frame generation when it comes to drastic changes between frames. We've added back in the native 30 Hz footage for reference. You can see during this crouch jump, the frame generation struggles to interpolate between completely different model locations. Time to get into new versus old model comparisons. Our previous performance testing video already showed that the new model has an FPS advantage, but here we're checking whether the new model looks any different. We'll stick to the worst case frame gen scenarios that we just identified. All of the comparisons are 2x old model versus 2x new model, because 2x is all the old model can do. Using the lightning flash scene in Veilguard, we can see that our capture using the new model exhibits more distortion around the text on the right side of the screen and the waypoint in the center. As we advance forward to the first real frame with the lightning flash visible, we can see that the rendered keyframes are basically the same. So, in theory, the generated frames should be as well. This could be a fluke though, so let's check other scenes. Examining the Final Fantasy hideaway scene frame by frame, there are clear differences between the generated frames for the old and new model, although deciding which is better is tricky. Any difference is an interesting result, since the rendered frames are identical and should create identical output. Generally, the new model has larger artifacts that take up more screen area in this scene, with clear outlines trailing behind the legs, so we'd say it's worse. It has a greater tendency to create chunky artifacts that look like bad compression. It also tends to have sharper outlines in anticipation of an object's location in the next real frame, which becomes obvious as Clive ducks to the side here, causing sharp outlines around his sword and legs. This leads to an aura of ghosting, both in front and behind the movement of objects. One area where the new model is unquestionably worse, even at full speed, is the UI artifacting visible in the Dragoon scene, where the old model has almost no problem handling the green health bar at the top of the screen, versus the new model's clearly visible duplication. When DLSS 3 launched, NVIDIA said that, quote, the optical flow field captures the direction and speed at which pixels are moving from frame 1 to frame 2, end quote. So it makes some sense that skipping the optical flow accelerator would cause problems like this. It's not all bad though. One of the most obvious problems with frame gen is that static UI elements appear outlined as the algorithm tries to cope with movement behind static text, especially with transparency or drop shadows. As you can see in our Veilguard steps scene, the outlining effect may be slightly reduced with the new model. On the other hand, text distortion is significantly worse, confirming what we saw during the lightning flash. Finally, we have Jedi Survivor. This game has mandatory TAA, which makes isolating frame gen artifacts more difficult, and it has no in-game render rate cap, so we had to use NVIDIA's driver controls. Still, we were at least able to get footage good enough for a frame gen model comparison. The old model may be slightly worse about creating bright outlines as Cal moves across patches of darkness on the stairs and after jumping away from the billboard. But the new model creates broader smudges around his boots and a constant sketchy outline around his legs as he moves in front of lighter colored surfaces. It also causes sparkles as Cal moves behind the white subtitle text. further UI issues that the older model doesn't exhibit to the same degree. Now we're going to get into the conclusions for everything all at once. We're going to kind of condense a bunch of mini conclusions and put them all here. First up, super resolution for CNN versus transformer. Speaking strictly to super resolution upscaling, the new transformer-based model is usually a slight visual upgrade over the former CNN-based model, but it should be viewed as a very mild trade-off for now. Like we said earlier, only the most obvious divergences between models are even visible when playing the game at normal speed. Given that caveat, the transformer model provides clearer visuals in most scenarios, though sometimes verges on coming off as a glorified sharpening filter. It generally keeps objects in motion more discernible, however, ghosting is hit and miss. In situations where the object in motion is already in sharp relief, like with the wires against the sky in Cyberpunk, or contrasting vibrant colors of Marvel Rivals, the transformer model exhibits reduced ghosting. Since these are some of the most distracting upscaling artifacts, it's a clear improvement in that regard. However, Final Fantasy XVI exhibited severe after images and smearing in situations where both the object in motion and the background were dark and detailed. With the current presets, the transformer model is generally worth it, we think, over the CNN model in terms of image quality in most games, and that is from the slower single-player games up to the faster-paced FPS type games or third-person shooter type games. Since the newer model, though, as we showed in the last video on this topic, has a slight performance hit of roughly 5% relative to the CNN model, we don't think it's currently worth it when already using upscaling in highly competitive games if every single frame matters to you and therefore the latency reduction matters to you. If you're genuinely hyper competitive though, you're possibly not using DLSS anyway. There's some possibility for change here going forward because NVIDIA says it's going to keep putting out new models for DLSS. And so transformer might get replaced with something else or just updated or whatever in the future. And they're looking at it as a jumping off point. So we'll revisit if those are significant. They should be positive changes as they refine it generally so far. That's what we're seeing CNN the transformer. As a brief aside on DLSS versus forced anti-aliasing, we had some thoughts on that. It wasn't the intent of the piece, but here they are. Cyberpunk exhibited horrible temporal stability issues at native that super resolution cleared up. Native should never look worse than an upscaled lower resolution, and game developers should not be complicit. They should be ashamed for letting this happen. Games should always let the user turn off anti-aliasing, if not include multiple AA options. At 4K, the pixel density is such that it barely has a practical impact anyway. If you're unhappy with overly soft or temporally unstable visuals in your games at native resolution, because maybe the game is just like that, try turning on upscaling at the least impactful level just to override the built-in anti-aliasing and see if you like the look better that way. NVIDIA's DLAA is just super resolution at a 100% render scale after all, and AMD's got some options you might like as well. And Intel has options as well for that point. So next up, frame generation old versus new model as the mini conclusion. So the new frame generation model appears to be a visual downgrade, but it comes with a small performance boost and a glimmer of hope that frame generation could maybe one day be enabled on the 30 series. If they don't want to just force you to buy the 50 series. The new model is also tied to MFG. So if you want 3x or 4x frame gen, you only have one choice. You also only have one choice in games that natively implement the new model. The only official place where you can choose between models is the driver level override menu for games that NVIDIA whitelists. If you have an Ada GPU that can't do MFG anyway, so that'd be the 40 series, you should consider sticking with the old frame gen model and taking the performance hit. If you have a Blackwell GPU, the 50 series, the benefits of higher performance combined with the ability to use MFG 3x or 4x likely outweigh the visual downsides. Now, that statement is assuming you want to use any of these, because there are plenty of people who just don't, and that's totally fine, and we've talked about that in our reviews. I mean, there's a reason our reviews kind of focus on not using this stuff, because we kind of look at it as close to the raw performance as possible in most situations. So that is assuming you actually want to use any of this. You don't have to. MFG 4X has the potential to look worse than FG 2X in situations where frame generation already struggles. That's because in a situation where MFG is running at its maximum 3-to-1 capacity, the AI frames containing artifacts are on screen for a greater proportion of time than they would be at 2x. The examples we've shown here push frame generation to its limits. Ideally, you want a high frame rate to start with. We talked about this in the last video, but it's not supposed to fix like a 25 FPS and make it feel suddenly really playable. It's more of a smoothing thing, but we talked about that last time. And playing with a higher frame rate to start with should minimize the artifacting that we've seen today. If you own a Blackwell GPU and you've already found situations where frame generation 2x works well for you, there's no reason to avoid 4x. However, frame generation is pointless if it exceeds the refresh rate of your monitor. So if MFG pushes your FPS beyond the refresh rate of your display, you should consider 3x or 2x instead, or disabling frame gen altogether to reduce performance overhead, because there is some. I think that gets into some of the confusing aspects of it as well, so check really seriously if this is an interesting topic to you. The previous video goes into all that. This is a hugely complicated subject now, and NVIDIA's made it very difficult to try and cover it in any sort of depth in a concise way. So it's just they're doing a lot with DLSS. So hopefully that helps out with what all this looks like. We're gonna leave it to you, of course, if you wanna turn it on or not. This is hugely subjective, that's why we're doing image quality here. So we give you the images, we point to the differences, up to you to decide if you hate it or not. For our testing purposes, we will not review video cards using completely arbitrary amounts of multipliers for frames in normal comparison charts where we're doing A/B comparisons of competing vendors. It's pointless. We might as well just type the number into a calculator and put that on the chart. And there's lossless scaling for frame generation. We want to look at that too, where now you just punch it up to 20x or something. Why not? Why not 1,000,000x frames? So for our purposes in comparisons, we're going to keep doing the reviews mostly the way we are. Now we do have the ray tracing sections we've added for all three vendors where we test. We have thermal, power, acoustics, raster, sometimes Schlieren, stuff like that. And then we've got ray tracing in there, power efficiency in there as well now. And we will keep looking at DLSS, FSR, XESS, and talking about that in the reviews. Just trying to set the sort of expectation now. Don't expect like a normal bar chart of performance with one that has an MFG something X in it, because that's pointless. Like that's not how you compare devices, unless you're NVIDIA, which is how they do it, because they want to make 5070 equal or better than 4090. So that's it for this one. Subscribe for more if you want to support this type of testing and our look at image quality and the comparisons and our commentary and all that. Go to store.gamersnexus.net. We currently have a coupon code active for when we launched our fan tester content, finally. And the coupon code is about fucking time. It'll give you 10% off anything on the store that supports this kind of content, specifically this DLSS image quality stuff. This is really expensive for us to make because it involves so much of the team and a lot of time to really crawl through it. The QC is really heavy on the video side. And I think we're at like 100 hours of combined work between all the writing and testing we did on this. A lot of testing, a lot of QC. And so it's big content for us, but we really like doing it. It's fun. It's interesting to look at new technologies regardless of how good they are or aren't, and it's up to you if you like it or not. Subscribe for more. We'll see you all next time.